So on this one, we're looking at the limit of the difference quotient as h approaches 0. And this occurs frequently in calculus because when you do this, you're finding the derivative. Anyway, what I want to do first, this isn't a bad problem at all. I know what f of x is, and I'm going to use f of x, but I don't know what f of x plus h is. So I'm going to find that really quickly. So f of something is something squared. So f of x plus h is x plus h squared. I do need to simplify that down really quickly, because in the form that it's in, it wouldn't be productive to go ahead and put it in the difference quotient like that. You'll do better with your difference quotient if you have simplified that x plus h down. So we're just going to say x plus h times x plus h, and you have to FOIL that to get x squared plus xh plus xh plus h squared.
Okay. And then you just simplify it together?
Yes. Okay, so now that we have f of x plus h, I'm ready to plug in the limit as h approaches 0 of f of x plus h, so x squared plus 2xh plus h squared. And sometimes I put it in parentheses just to sort of block off which section I've done. Minus the x squared all over h. So let's carry our limit notation with us. We're not ready to directly substitute yet. We haven't canceled anything. So what is going to end up happening is our x squareds will cancel because it's a positive and a negative x squared. And you have 2xh plus h squared all over h. And this h in the bottom will cancel, but because everything up top has a h in it, this power of h will cancel one of those h's.
I thought it just cancels out the squared one.
No, because let me actually write it a different way. What you could do is think about factoring out the h and being left with 2x plus h.
Oh yeah, that's what the
all over h. And so yes, the squared is gone, but the h from the 2x is gone as well. So we did have some cancellation. I could go ahead and directly substitute. I'm just going to clean it up though. And to directly substitute, you're plugging in a 0 for h. So the limit as h approaches 0 is 2x. Since the question told me what x is, it doesn't always tell you what x is. So if it doesn't tell you what x is, then you would be done at this point. But since it told me what x is, I'm going to use that extra bit of information and plug in the negative 8, which was x. So we get a final answer of negative 16. So looking at the graph, a lot of people do have trouble with the graphing questions because they're so easy to get wrong. They're so easy to look at it too quickly, you get it wrong, and then you think, oh, I have no idea. And so from then on, you're scarred about these graphing questions. Let's forget about the graph and just look at what it's asking us. Of course, we already know the answer. But it says the limit of f of x as x approaches negative 3 from the right side. It wants to know if that limit is equal to 9. Well, let's look at negative 3 from the right side. So you want to visualize like a boundary. You want to visualize this negative 3, okay? And so from the right side, what you could do is just kind of follow what the graph is doing as we are moving closer and closer to that -3 value from the right side. So I'm moving closer and I'm doing a whole lot of different things, but as I get closer and closer and closer and closer and closer to 3, or excuse me, -3, this y value is headed up here to this 9, and that's from the right side. So that's why that statement was true.
When do we know to look at the line at the bottom or the actual graph part?
And that's a good question. Right now, only looking at the graph and not seeing the true-false part, the question part, I don't know the answer to that. And honestly, this graph is so ugly looking because they want you to stress out about things like that. This question may not even ask about this. So it's almost like don't cross that path until you get there. And don't worry about if you're going to go there or not. Just take it a question at a time. So it may, but if it asks me, if it asks me the limit as x approaches 3, from the left side of 3, it would be +9. From the right side of 3, it would be 0. But it may not even ask me about that. Let's look. X approaches 0, 0, 0. And see, no, it actually never does ask about +3. And so you're never going to have to even worry about that part. The next part it asks about is when we are approaching 0. So I'm going to erase this line, and I'm going to kind of draw me a visual at the x value of 0. And so it's saying 0 from the left was 3, and that was false. So let's see what it really is from the left side of 0. From the left side of 0, first of all, f of 0 is equal to 3. But that's not necessarily what the limit is. In fact, that isn't the limit. Because as we are approaching the green line, as we are approaching 0 from the left side, those y values are getting smaller. They're getting smaller. They're going to 0. From the left side, they're going to 0. They're actually going to 0 from the right side as well. So the one-side limit from the left is 0. The one-side limit from the right is 0. That means the two-side limit is 0 as well, which is kind of odd because at exactly 0, the y value is 3. But that shows you the importance of limits. The limits are all about as you get close to what's happening. It doesn't care exactly about what you do at that instance. It's caring what's happening as you are getting close to that value.
Okay. At the open circle, it would be a limit of 0. Is that what you're saying? And then at the open circle.
Yes, but now it's not because it's an open circle. Almost okay, so I have that line highlighted, but let's not highlight it, and let's make it black. Let's completely go through it, okay, and pretend that we don't see the open and closed circle. I don't even know if it's defined at 3 or not, okay? Because the value, 3, it's 0, I'm sorry. I don't know if it's defined at 0 or not, because the thing is, I don't care what's happening at 0, exactly at 0. I care about what's happening as I'm getting closer to 0, as I'm getting closer and closer and closer and closer to 0. It's a roundabout type thing. Okay, so the limit as x approaches the x value of 0 is 0, because, from the left side it approaches 0, from the right side it approaches 0, and that two-side limit is 0 as well.
Okay.
And basically, to write down what I said, the limit of f of x as x approaches 0 from the left is 0. The limit of f of x as x approaches 0 from the right is 0. Therefore, the limit of f of x as x approaches 0, and it doesn't indicate from the left or the right, so that's the two-side limit. Because our answer for these two things were the same, then this is going to be what that answer was for both of those. This is a really good problem for several reasons. So with functions being continuous to me is almost like it's a good thing to be continuous. It's not necessarily a good or bad thing. But with that mindset, I kind of go into every situation kind of assuming that it is going to be continuous until I find something about it that raises a red flag. Kind of like, it's almost like I'm always going to trust somebody until they do something that, makes me sort of suspicious. Well, what's making me suspicious here is not necessarily the sign, the trig function of sign. That's not necessarily what's making me suspicious, because the trig function of sign is actually, if you Google the image, it looks something to the tune of that, and it is continuous. So that's not what's making me suspicious. What's making me suspicious is the fact that I have a denominator. This is rational. And I know that, no, I can not divide by 0. It's okay to have it in the numerator, but you can't have 0 in the denominator. Well, there is a function in this denominator, and there may be a value of x right here that makes sine of that x equal to 0. And so that would be an issue. So I need to know where sine is equal to 0, because wherever sine is equal to 0 at, that is where this function will not be continuous. So let's move over to the unit circle. This is something that you will have for your test. In the testing lab, you can just, whenever you're taking your test, ask the lady at the front for a copy of it, and she may ask you what class you're in, but she'll end up giving you one. Anyway, on the way that we read this, just know wherever we're placed at, these values here, think of them as coordinates, and the cosine will correspond with the x coordinate, and the sine will correspond with the y coordinate. So I want to know where sine is 0. So where is my y coordinates 0?
At 2 pi.
There is going to be 0 at, let me do the highlighter, right here. When we're starting off, it's 0 at pi. So 0, where you start off, 0 at pi, and then you keep on reading this. You go counterclockwise as you're reading this. So keep on going. I'm not seeing any more 0 coordinates, 0, 0, 0. Now, the 0 right here is an x coordinate. So we keep on going, 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 and we end up where we started at. But this goes from 0 to pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. It's intervals of pi. Now, that may seem confusing the way I'm just like rotating around, but think about it as laps. Like you're gonna run this track, okay, and this is a mile. So the other half is a mile as well. So it's like 1 mile, 2 mile, 3 miles, 4 miles. That's sort of the same idea that we're going with, and so anyway, we're going to have a y value, a sign of 0 every time we have that interval of pi. So when we're selecting our answer, it's saying where is it continuous. Now I don't really like this option A at all. It doesn't make sense. None of these sounds like it's never continuous, but none of these is saying that these answers are wrong, that B, C, and D are wrong. So let's look at B, C, and D. Continuous at x equals 0. Now that's tempting, because we know that, this needs to be 0 down here, but it's where the sign of x is 0, and sign of x is 0 at those intervals of pi. Literally pi, 2 pi, 3 pi, and so forth. Continuous everywhere except that. So that's why this is the answer. Now, let me explain what option B means. Everywhere except pi over 2, 3 pi over 2, 5 pi over 2. That is right here. 1/2 pi is equal to pi over 2. So if it were at intervals of pi's over 2, it would be like 1 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. So that's like at every quarter, but that's not the case. It's at every pi. Let's look at a question that is really the same type of question, and you're going to look at it and you're going to be like, this is something completely different. But it's really the same type, and it's this right here. At what points, if any, is the function discontinuous? Well, you're like, whoa, this one doesn't have any trig in it. Well, no, it doesn't have any trig, but it's a question about continuity. This one up here was asking about where is it continuous. So it's like, okay, where are we continuous? This wants to know, instead of where are we continuous, where are you not continuous? So if this one up here asked where you were not continuous, you would say, I'm not continuous at intervals of pi and 2 pi and 3 pi, etc. You see how that answer is almost the exact same? Not continuous at this, and then anyway. So they're really the same type question. Now, again, I do realize the one that we just did had trig in it, but it wasn't the trig that really determined the continuity. It was the fact that something made the denominator 0. So with this, again, I look at a function and I automatically assume, oh, this is probably going to be continuous until I see red flags. So let's talk about the red flags I see. I see something in the denominator, and I see a square root. And that square root just so happens to be in the denominator. Well, I know that in a fraction, the denominator cannot be 0. So that's one stipulation. And I know that in a radical, when you're taking the square root, you can't take a square root of a negative number. So that means your value that you get for the square root of x must be greater than, the x itself inside of the square root must be greater than or equal to 0. So numbers greater than 0 are positive. So it can be, I can take the square root of a positive number. I can also take the square root of 0. I can't take the square root of anything that's less than that. Okay? So what I have to do is sort of marry these two. Marry these two stipulations. They have to agree with one another. So x cannot be 0. If you're looking at the number line, let me make it a different color. If you're looking at the number line, x cannot be 0. Well, you could have a graph. Here's 0. You could have graph that way, but it wouldn't include 0, right? But now for the square root of x, if it has to be greater than or equal to 0, you could have a graph greater than 0, and then it could include 0. So where do these two things agree with each other? Well, they don't agree with each other right here, okay? Because basically, where do I have graph on top of each other? Where do I have overlap? Okay, is what I'm looking for. I have overlap right here at greater than 0. But you see, this doesn't include 0, but the other does. So when I'm working this problem, my x's must be greater than 0. Not greater than or equal to, but just greater than. Because one says not equal to 0, one says greater than or equal to 0. So we're going to go with your greater thans, but we're going to respect this person's not equal to. And so when we're solving this, we're respecting their greater than. But since the other one was not equal to, we're not going to include the or equal to. Okay? So the inside of this root right here is what we're worried about. And I keep on saying x's, but really it's the u plus 6. Okay? Am I worried about the 9u plus 7? No, because that was not in the square root and that was not in the denominator. I'm not worried about that. So u plus 6 greater than 0. And honestly, I did a whole lot of talking right here, didn't I? A whole lot of talking. All you need to do is memorize. If you have this problem with a square root denominator, take that denominator, the inside of that root, and set it up like this. That's all you need to remember. Okay? So to solve it, subtract 6. U is greater than negative 6. Let's graph that really quickly. So we can write an interval. Here's negative 6. Greater than negative 6 would be from negative 6 to infinity.
Okay, yeah, I see that.
And let's make sense of it real quick. From negative 6 to infinity. Anyway, numbers from negative 6 to infinity, that would include things like negative 5, negative 4, negative 3, negative 2, 1, 2, 3, 4, 5, okay? Well, let's look at negative 5, okay? If I plug in negative 5 right here for u, negative 5 plus 6 is positive 1, right? I can take the square root of positive 1, which is 1, and I can also divide by 1. So we're good. But numbers outside of that interval that we just found as our answer, this is the answer, by the way. Negative 7, for instance, would be outside of that answer. Negative 7 doesn't work because negative 7 plus 6 is negative 1, and you can't take the square root of negative 1. Undefined. The limit as x approaches 0 of this function right here. So I'm not freaking out yet. It's ugly, but I'm just kind of going with the flow. I love that it just gives me a hint right here. This is a rule, sine of theta over theta. If we have that and theta is approaching 0, then that is equal to 1. Well, that's definitely not what I see here. Okay, but let's manipulate it. Let's make it look different to see if this could be found in this. So how am I going to manipulate it? How am I going to make it look different? Well, I'm going to write everything in terms of sine and cosine, meaning if there's a trig function in there that is not sine or cosine, I want to rewrite it. Okay, here's a few identities you should recall. And you won't really need a lot of this knowledge for the test. Know that tangent, and let me change my color. And that's not changing the color, Johnny. Okay, tangent of theta is equal to sine theta over cosine theta. Theta, by the way, you might as well just pretend that's a variable. Cosecant of theta, secant of theta, and cotangent of theta. Let's recall those really quickly. Cosecant is 1 over the sine of theta. Secant is 1 over the cosine of theta. And cotangent is 1 over the tangent of theta, which could also be cosine of theta over the sine of theta. So just kind of know those things. So basically what I want to rewrite here is the cosecant. Anyway, so this is the limit as x approaches 0 of x. And first of all, you can rewrite this as x times cosecant of 4x times 1 over the cosine of 2x. In fact, that may help you, because if I multiplied all of this together right now, x times cosecant 4x times 1 over the cosecant of 2x, you would multiply numerator, numerator, numerator divided by denominator times denominator, multiplying straight across to end up with this same thing. So I am going to rewrite the cosecant function in terms of sine and cosine. Cosecant is equal to 1 over the sine So before we go much further, you're probably thinking, okay, you've rewritten it in terms of sine and cosine. It still doesn't look much better though, right? But we're making a lot more progress than what you're thinking. I probably should have explained that the limit of the sine of theta over theta as theta approaches 0 is equal to 1. But the limit as theta approaches 0 of theta over the sine of theta is equal to 1 as well. Okay? That being said, let's go back down here and look at what we have. We have 1 over the sine of something, right? So I'm starting to feel good. I'm starting to feel like maybe this could go away and go to 1. But I need whatever it's the sine of, whatever it's the sine of, I need that exact same thing to be able to be in the numerator. And right now, is there a 4x in the numerator somewhere? No. There's an x, there's a 1, and a 1. But there's not a 4x. There's an x, but not a 4x. So what are you missing? You're missing a 4. Well, can you make a 4 be there out of thin air? Yeah, you actually can, by multiplying the thing by 4 over 4. Right? Because you multiplied it by 1. And so therefore you did not change it. You manipulated it. You're being sneaky. Okay? So let's look. The limit as x approaches 0 of, we'll just write x times, I'm just going to multiply it all out, okay? 4x, 4 times, well, x times 4 times 1 is 4x. All over 4 times the sine of 4x times the cosine of 2x. And this section right here goes to 1. And basically, all I have to look at now is the limit of 1, because there's nothing left in the numerator, over 4 cosines of 2x as x approaches 0. From the 4 over 4, this 4 was left in the bottom. Now I used the 4 in the top for my rule, okay? But the 4 is left in the bottom, and we also have the cosine of 2x. Anyway, so now think about use direct substitution basically. What is the cosine of, and then since I'm using direct substitution, I will not use limit notation. Two times 0 is 0. The cosine of 0, you can think back to that unit circle, but cosine will be 0 at whenever cosine is at the value of 0. Right here, this is the value of 0. Pi over 2, pi, 3 pi's over 2. Anyway, 0 being right here, that cosine value is 1. The sine value at 0 is 0, but the cosine value at 0 is 1. So cosine of 0, all of a sudden you have 1 over 4 times 1, which is 1/4.